Imagine building a great pyramid, imagine a Roman aqueduct. Our ancestors were brilliant engineers. They used simple tools, they used chains to measure distance, they used compasses to find their direction, they relied on their eyes, they relied on their hands, they relied on their sheer ingenuity. For millennia, this was the state of the art. Surveying a piece of land meant walking it, painstakingly measuring every rise and fall, painstakingly measuring every twist and turn. It was a slow, laborious process. It was subject to human error, subject to the subtle shifts of the earth, subject to the limits of our own senses. But it was the best we could do, and with it, we built civilizations. Now look up, look to the stars. The same cosmos that guided ancient sailors now guides our grandest engineering projects. We have extended our senses far beyond our planet's surface. What is a satellite? Think of it as a human-made moon. It's an object we launch into space. We place it in a precise orbit where it circles our planet. Some satellites are telescopes like Hubble. They peer into the deep universe. Others are communicators, bouncing signals around the globe. But a special class of satellites looks back at us. Among the most transformative is the Global Positioning System, GPS. Each satellite carries an incredibly precise atomic clock. As they orbit, they continuously broadcast their exact position and exact time. Your phone picks up signals from multiple satellites. A surveyor's receiver on the ground does the same. By calculating tiny differences in signal arrival times, the device triangulates its position on the globe with astonishing accuracy. Systems like INSAR, Interferometric Synthetic Aperture Radar, add new powers. INSAR can detect ground movement as small as a few millimeters from hundreds of kilometers up. See a dam wall bulge slightly. See a volcano flank swell before an eruption. See a city block slowly sink over time. This is not science fiction. It's the power of remote sensing. Satellites give us a God's eye view, monitoring vast and remote areas continuously. They offer a perspective that is global, precise, relentless. Having incredible data from satellites and ground sensors is one thing. Getting that data to the people who need it, when they need it, is another challenge entirely. This is where the unsung hero of our story comes in. GPRS, the General Packet Radio Service. Think of it as the delivery system, the digital courier that works tirelessly in the background. GPRS was a key step in the evolution of mobile networks, a precursor to 3G, 4G, 5G. It allowed data to be sent and received over the cellular network in small packets, like a series of digital postcards. Before GPRS, retrieving data from a remote sensor often meant physically going to the site, plugging in a laptop, downloading the information. That could take hours or even days. With GPRS, a sensor monitoring a dam's structural integrity or a landslide-prone hillside can automatically send a small packet, a status update, every hour, every minute, every few seconds. That packet travels wirelessly through the cellular network and arrives almost instantly at a central server. An engineer hundreds of miles away can view a live dashboard of a project. If a sensor detects unusual strain in a bridge support or rising groundwater pressure behind a retaining wall, an alarm can trigger immediately. That enables proactive intervention instead of reactive cleanup. GPRS is the central nervous system, linking remote sensors back to the engineering office, turning concrete and steel into living, responsive systems that warn us before danger strikes. Surveying and geotechnical engineering have always been siblings in the family of civil engineering. The shape of the land, the boundaries of a property, the position of a structure, the type of soil, the strength of the rock, the behavior of groundwater. Traditionally, these two disciplines worked sequentially. A surveyor would map the land, a geotechnical engineer would drill boreholes and take soil samples. It was a partnership, but a slow and disconnected one. The surveyor's map was a static snapshot in time. The integration of space technology and real-time communication has fused these two fields into a dynamic, interconnected discipline. A modern surveyor armed with a GPS rover doesn't just map a point once, they can map it continuously. By setting up a GPS station on a construction site, they can track the movement of the ground or the structure itself in 3 dimensions, in real time. This is where surveying crosses over into geotechnical monitoring. The surveyor is no longer just drawing a map, they are creating a live, 4-dimensional model of the project, with time as the 4th dimension. The most obvious is accuracy. Combining precise satellite positioning with on-the-ground geotechnical sensors provides a complete and highly accurate picture. We can correlate a tiny surface movement detected by GPS with a change in underground water pressure measured by a piezometer. This allows engineers to understand the cause and effect relationships within the Earth, moving from simple observation to predictive analysis. It's the difference between knowing a patient has a fever and having a full diagnostic scan that shows the source of the infection. Automated remote monitoring reduces the need for personnel to enter hazardous areas, unstable slopes, deep excavations, active construction zones. Instead of sending someone to manually read a gauge on the face of a dam, we can get that data beamed directly to our screens. We are building on a foundation not just of rock and soil, but of pure, unadulterated data. Consider the construction of a modern highway or railway line. Today, engineers start with high-resolution satellite imagery and LiDAR, light detection and ranging data. LiDAR uses laser pulses to create a detailed three-dimensional map of the terrain. This allows them to plan the optimal route from their desks, minimizing environmental impact and construction costs before a single worker sets foot on the ground. In urban planning, this technology allows us to build smarter, more resilient cities. By using satellite data to monitor subsidence, the slow sinking of land often caused by groundwater extraction, city planners can identify areas at risk and enforce stricter building codes or manage water resources more effectively. For major construction projects like digging a new subway line underneath a bustling city, a dense network of GPS receivers and tilt meters can be placed on surrounding buildings. This continuous monitoring ensures tunneling isn't causing damage to the historic structures above, providing peace of mind to both engineers and the public. The world of mining has been completely transformed. Open-pit mines are essentially human-made mountains, inverted. The stability of their massive terraced walls is a matter of life and death. Radar-based satellite systems and ground-based robotic total stations continuously scan the pit walls, detecting movements down to the millimeter. This data, transmitted wirelessly via GPRS or other networks, feeds into software that predicts potential collapses hours or days in advance. This enables the timely evacuation of workers and equipment, turning a potentially catastrophic event into a managed, controlled one. For hydrology and dam management, satellites provide critical information. They can measure snowpack in remote mountain ranges, allowing engineers to predict the volume of spring meltwater that will flow into a reservoir. This helps them manage dam levels to prevent flooding while maximizing water storage for irrigation and power generation. Meanwhile, sensors embedded within the dam itself monitor internal pressure and structural health. Terry Dam, one of the tallest dams in the world, located in a seismically active Himalayan region, is embedded with a vast array of geotechnical instruments. The Delhi Metro project extensively used robotic total stations, tilt meters, and settlement markers, providing constant data streams to track ground movement in real time. Japan has developed one of the world's most sophisticated landslide prediction systems, using sensors that measure rainfall, soil moisture, and ground movement. When data indicates critical conditions, automated warnings alert communities via sirens and mass text messages, providing crucial minutes for evacuation. This is the new paradigm of engineering, a shift from reactive to proactive, from static to dynamic, from isolated to integrated. As powerful as today's technologies are, we are only at the beginning of this journey. We are standing on the cusp of an even greater transformation. It's driven by the convergence of several new and powerful forces. The future of engineering will be shaped by the Internet of Things, artificial intelligence, and next-generation networks like 5G and space-based internet. The Internet of Things connects everything, not just phones and computers, but every lamppost, every water pipe, every bridge beam, to the internet. Imagine millions of tiny, cheap sensors embedded in a city. They create a torrent of data, a real-time digital twin of the city. We can monitor the structural health of bridges, traffic flow on every street, and water quality in pipes simultaneously. GPRS was the footpath. IoT powered by 5G will be a multi-lane superhighway for data. This is where AI comes in. No human team could analyze that volume of data. AI can, in real time, identifying patterns, predicting failures, and optimizing performance. AI could predict a water main break days early by spotting pressure and acoustic changes. It could reroute traffic dynamically to prevent gridlock. It could optimize a building's energy based on weather and occupancy. AI becomes the master conductor of smart infrastructure. Our connection to the cosmos grows closer. Space-based internet constellations like Starlink remove communication black spots. An engineer can get high-speed data from a sensor in the Sahara, in the Amazon rainforest, as easily as downtown Manhattan. This unlocks global-scale engineering and environmental monitoring, The fusion of space technology, ubiquitous communication, and artificial intelligence promises infrastructure that's born intelligent, adaptive, and resilient, creating a safer, more sustainable world for all of us. Space plus networking plus geotechnics equals smarter, safer engineering.